Rajkumar ji, kindly start the second session of your presentation.
Okay, sir, sure. We can start the session right now. I will, before I start, let me change my sound settings to system. I will select my headset.
Okay, so let us start. I will. I hope everyone can hear my voice right now with a lot of noise. So the reason is I'm just going to play a video. I'll just share my screen. Share screen. I hope everyone can see my screen now clearly. Okay. And what I'll do is I'm going to show the capabilities of the KUK robot. Okay, so basically this robot, even though it's used for industrial purpose, okay, so in order to show how responsive this robot is, in order to show how responsive this robot is, okay, they have created this technology demonstration video. Okay, it's basically making the robot play ping pong. Okay, so how fast it's going to work. So please listen to this. So basically, a table tennis guy called Timo Boll, okay, he is going to play this ping pong game with the robot. Okay, as of making this video, he was ranked #1 in table tennis. So he was invited to play ping pong with the program cooker. So of course, like right now, if you see, you can see the capabilities, but somehow at the end of this video, he manages to beat it by exploiting some problem, flaws with the robot, of course. So he will, instead of relying on the actual rule, okay, so like he tends to eat at the end of that, exactly at the line. So robot is not currently, okay, it's not able to sense this much precision. Okay, but of course, it is capable of doing that. But as of making this video, they haven't programmed to detect, this end line, this rule on top. Okay, so this Cougar robot was only, designed to detect the ball. Okay, so it's a very long video, so I don't want to play the whole thing. Okay, you can just go to Google and search for this Kimo bowl versus KUKA bot. Okay, so there will be full version video. Right, so let me just continue. And let me connect.
Yeah. So if you have any questions as of now, please do let me know. So right now we are able to simulate, okay, the effects of your KUKA bot inside the LabVIEW. So it makes total sense that you will also be able to control it. Okay, so previously I was trying to explain that what are the sensors data which you can collect from a virtual world inside LabVIEW. So we already saw that. Now we are going to see, the actual control of KUKA bot, okay, simulated version of KUKA bot with a full program itself. So I just started it. Okay, so developing it will take too much time. So I want you to focus on that. Okay, we still need to go for something else as well. So I'll just show what exactly happens here. Okay. So then you run the program. Okay, so it takes some time to set up. And ultimately it pops up. Yeah, it popped up. Okay, and here you have this KUKA bot. Okay, so controls of this KUKA bot, you can give the X velocity, Y velocity, everything. Okay, previously there were like three arrays, right? Three arrays of values you have to use to control it. Okay, but here you can see that instead you can give X velocity and Y velocity. Automatically it will calculate for us what should be the value of these four wheels. Okay, only the value of four wheels we can give. Okay, but there is an algorithm, okay, which will help us steer clear of those things. We'll see about that anyway. So by using this example, you can see, okay, like I can steer, okay, I can move forward in Y direction. Okay, it's moving forward. If I reduce it, okay, it's coming to 0. If I give it negative, it's going to go backward. So I can also use the angular velocity. Okay, I can turn it. Okay, I can move in Y direction again. Okay, after turning it, I can just give X direction. Front only it will move. So these things can be simulated. And more importantly, if I stop it, everything will stop. Okay, more importantly, you can also control, by using these functions. Okay, they also made us a way to control this joints as well. Okay, so everything is open. Okay, so that level of flexibility is available, okay, for us to control. Okay, so now, if I run this program again, it will automatically start to run forward because we have set the value as velocity as 2. Run. Okay, so it's at 0. Apart from that, if you see, you can also control the gripper as well. Okay, let me just zoom inside. So gripper also we can control. Open gripper. Okay, you can see the gripper opened. If I can press it again, it's going to close. So there is also like pick and place kind of thing is also available. Okay, you can totally simulate everything. Okay, you don't need to get the robot to do it. You simulate the setup, then basically you can build the robot once you are familiar with the algorithm. Okay, to check whether all these functions will work or not when you get the actual hardware. Okay, before actually getting the hardware, you can simulate the setups using this particular one. Okay, like for example, you can also control since this is having the joints. You can also control the joints as well, with the location of joints. So whatever fields, okay, whatever is required for us is going to control it. Option is going to be there. So now for the control, the application requires us to give the values of velocity of 1, 2, and 3, 4 wheels. Okay, but we human beings are only capable of giving like what is the velocity which it has to move forward or backward or left side or right side. Okay, so we cannot directly calculate what should be the value given to these combination of wheels in order to make the movement. Okay, so in order to play around, in order to translate what we speak and what the machine is going to understand, so we need to write some set of algorithms. So typically these algorithms could also be written by us, okay, if we have the knowledge to write the algorithm, or we can basically make use of some set of functions which are available as a part of the LabVIEW. A LabVIEW has some commonly required robotics algorithm already present, so you can basically make use of that and do your program. So yeah, okay. Previously I didn't save the code, so it's starting from first, but not a problem. I will just again one initialization of the motors. Okay, initialization of the motors. Okay, which can be done by checking the motor first. So I don't need to initialize it one by one. Okay, to initialize the motors, okay, I just have to first initialize the bot. Okay, in the robotics module, I'll have the bot, okay, to call you bot. Okay, I'll initialize the simulated version of it. Okay, let it load. So first I'll initialize this. So in order to initialize it, I have to name it. Okay, in the XML, okay, we already have the name of the bot. So it has been already named as ubot or not. If you add another Kuka bot, you will again get another robot. Okay, another robot, again another name will be coming. Okay, so for everything, different names will be given, IDs will be given. So as I was saying, there are specific algorithms, okay, which needs to be used. Okay, either you can develop your own algorithm, or for robot operations, you will have some algorithms that are created, like path planning, okay, like obstacle avoidance, steering, okay, robotic arm control. So for this, we'll be already having some operations, okay, present with it. So yeah, for that, now you can make use of whatever is required by us, right? So now, right now, if you see that problem which we are trying to solve, okay, is basically when we run the program, okay, we should be able to translate X and Y motion to something which can control the four wheels. Okay, so that is basically steering algorithm, okay, which we need to make use of. Okay, so using these algorithms, okay, which are available as a part of LabVIEW robot useful environment, we can make use of it. Okay, first, what we'll do is we'll make use of this U-bot. We'll initialize it. Then first we'll get the sensor data or the actuator. We'll initialize the actuator. Okay, we'll go to we have to work with KUKA there. KUKA. Okay, we initialize it, simulated one. Then I have to initialize the platform. We get platform because that's what we are going to help move it. So block by block programming can be enabled by using LabVIEW. Okay, so we don't have to explicitly type anything like in Python if you want to work, so we have to type it. So we don't do such complex typing stuff here. One thing what you do is you initialize the robot first, then you are saying from the robot I need only the platform. So platform's reference will be brought here. Then maybe you need to start with platform steering. Okay, for that we have to take one more reference. Okay, so it will extend one side at this location. Right, so this is only for platform steering. Okay, then we need to do something like set the wheel velocity set point. That's what we did last time. Although we are not able to control the movement of the motor. Okay, and in the demo program, okay, they were able to control it. We have to write a logic which will control the left and right. So the ultimate idea behind LabVIEW is we have to make engineers and scientists program the sequence, okay, not the program itself. Okay, already programs should be available and we should be able to put blocks and pieces of code together to do our job. Okay, so that's the reason why we'll be having these blocks already available, commonly required stuff. If you don't want to use this, then basically you can write your own algorithm, create it as a sub-VAR function, and make use of it. Okay, as simple as that. So before we directly connect this to CCW, okay, we need to first convert the x-axis and y-axis data to something which your robot can understand. Okay, so for that, what we do is we will go to robotics, the steering. Then we'll be having functions called as frame to motor. Okay, so this will calculate the frame to motor information. Okay, so by using this, you can calculate it. But first, we need to take the frame out, okay, and give it as a reference. Then steering velocity is basically x-axis and y-axis and angular velocity. Okay, this you can basically create as some controls, okay, or knobs, whatever you feel like is better. Okay, I'll use a vertical slider, which I'll have it as 0.3 meter per second. So let's say this is the x-axis. Okay, I'll have something like y-axis, or that I'll have an horizontal slider. Okay, I want the angular velocity. Maybe let me have like knob. Okay, this could be to 10 or 20, whatever. All these three values we're going to, this velocity should be converted into something motors can understand. All three motors can understand. So basically what I'll do is I will, combine all this data, x-axis, y-axis, velocity, and these three by using this build array. Okay, I'll combine all these three things and put it inside. So what this will do is, okay, when I give x-axis, y-axis, z-axis steering data, okay, I have to develop an algorithm which will convert this to something your motors can understand. All these four motors can understand. So when I say go front, okay, your four motors should work in a particular way that is going to move forward. Or let's say if you want to move sideways, okay, it has to rotate in such a way that all four have to rotate in such a way that it has to go sideways. Okay, or if I want to rotate, okay, if I want to make an angular movement, I have to adjust in such a way that all four motors should be working some way. And doing this manually is going to take a lot of time. Okay, so internally we have to do some calculations, like x-axis means 1, 2, 3, 4 should go front, and minus means it should be subtraction, okay, backwards. So instead of us doing this calculation, there are existing algorithms like this. Okay, this is why algorithm is used, so which we can use to do our stuff. So when I give this will come outside. Okay, set points will come outside in radians. Okay, this I will make use of and give it as input. Instead of me calculating this 4 values, okay, this will calculate it for me and give it to me. So where I have to apply it, I have to apply it in the mobile platform. So to that, I'll just send the motor reference alone, and this will take care. Okay, so that's how you can make use of references, okay, algorithm. Okay, for each and everything, there are different types of algorithms available. And now, next is going to be, you should also be able to read back data. Okay, so you can either read the data here itself, these are set points, but what is the current, speed? If you want to look at it, there is going to be something like in KukaBot, okay, platform, it says something called get motor velocity. Okay, this is set point, but what exactly is current speed? If you want to know that, internally this KukaBot will have a rotary encoder, everything will be there. Okay, it will be calibrated and it's just going to read us the current speed and give it to us. Of course, in simulation also it applies. So one thing you have to understand is the code which you're writing right now is not only for your simulated function. Okay, so one thing, the change you have to do is after you get the actual hardware, okay, and the hardware is going to add this function, so it is more robot. Okay, the only thing you have to change, absolutely change is in your robotics, simulator or sensor app. Okay, we have to change only like in the KukaBot. Only thing I have to change is instead of using the simulated KukaBot, you have to use an actual KukaBot. And when you connect an actual KukaBot, okay, it search for the KukaBot, okay, whether anything is connected or not, and it will return the same reference as to what we have to connect. Okay, and potentially we'll get multiple KukaBot. Okay, so this will be like multiple KukaBots will be there. So that also we have to configure. Okay, predominantly for one EtherCAT, okay, the KukaBots are connected to your computer via a section called as EtherCAT. Okay, using that, you'll make the connection and it will be able to connect. Okay. So to get the current velocity of motor, this is going to give us in terms of rads per second. You can of course convert this rad per second again to something which you can understand, okay, to the meter per second. And again, to convert rad per second to meter per second, you know the calculations, you can do it manually. Okay, but if you see robotics, Cookabot, not here, okay, in steering, you have something called motors to frame. So here we get in terms of rad per second. We can basically convert this data, whatever data which we get, into something which we can understand. Then once we are done, ultimately we can close it up. In your robotics, we have something called Cookabot, close Cookabot. We have to give the reference. That reference can come from below. So you can type to here. Still your program is not capable of running. So if your program is not capable of running, you have to double click on it and see what exactly is happening. Let's say something like one or more sets of this. This needs to be wired. Yeah. Now if you see it's going to work. Now if I run this, you have to close the steering. Okay, create platform steering is done. Probably there will be a way to close it off. Okay, so where do we do it? Again, we have to go to robotics, look about platform, get platform is there. Okay, but there is no way you can close the platform. So closing the Cookabot will close everything. Okay, both of them are linked together. So let's try this out. You can see if we are getting any errors. If you are getting any errors, then the code is wrong. So on this, and where is the window? And window is opened. And this is the current velocity. I can move in y-axis. Okay, it's not moving. Okay, that's strange. So let's try that again. So when I run this, it should move. It's moving due to initialization problems. Okay, during initial time, okay, the Cookabot will move on its own. Okay, but when you give some data, it's bound to move. If it doesn't move, there's some problem with the program. Okay, so we have to debug it. Okay, so first we get the mobile platform. Okay, then from the mobile platform we will get the information regarding the platform steering. Then we apply the two motors. Okay, but if there are any problems, okay, then we have to check it out. Okay, like we have to check what values are going into the motor. So that can be done by creating indicator over here and check what are the rare values are going. And run this, you should be able to see clearly. It's going as 0. That means that maybe there is some error. No. Even after setting these values, okay, there is no values which are coming outside. Okay, this is angle. Sorry, we have to set the velocity. Let's try that again. Okay, now it's moving. So that means this get the angular after 0. Now it's going to go straight. Let me stop it. Y-axis. Okay, so minus 0.3 to plus 0.3. Moving it in y-axis, will move it in the y-axis. Okay, back and forth. So it will interact the obstacles. So if it is 0, it will stop. And if I want to go to x-axis, also it will go. Okay, but 0 is too much, so I have to set like 0.3 and minus 0.3. Basically, by setting 0.3 and minus 0.3 x-axis, it will move sideways. Okay, and you can see that the combination of that will set up different values for x and y. So, yeah. And the reason why here, even though we set 0.3, immediately it will not go to 0.3. Okay, so it will take some time. That's why we'll be having, we'll be taking readings of the current velocity as well. Set point is different, current velocity is different. Sometimes we need to do a closed loop system. Maybe we need to use the control system to check whether whatever you're setting is getting achieved or not. Okay, in different load conditions. Okay, so whatever load condition is, depending on the need, okay, your system should adjust itself and come to the set point, and it should maintain the speed. So for that, we'll be implementing control systems if you want. Okay, that's why they say add code here. Whatever code you need to add, okay, it could be added. Okay, so that's basically what we are supposed to see in this simulation. Right? So if you have any questions as of now, please let me know. Then we'll see about information related to how we can approach for implementation. Okay, simulation is good. Okay, so we can create models, like also other models available, okay, which we can simulate. But ultimately, our goal is today we are able to simulate. Tomorrow, after preparing the components or making the code, what is the system which we are going to use to control it? So that level of implementation level we should be having idea. So materials. I'll check with my team and I'll discuss. So there are other types of algorithms, like let's say right now we are seeing examples related to, steering. Okay, there is something called extended Kalman filter. Okay, so which will basically, filter out noises, okay, from sensor. Okay, the noises, these sensors are basically used for localization. Okay, to find out where exactly this, uh, you know, uh, to sense where the exactly the, where is it exactly the reference is. Okay, so in order to create the closed loop system, okay, basically a sensor should be with less, noise as required. Okay, but if you saw previously in the simulated model itself, okay, in virtual model itself, you saw a lot of noise. Okay, the KUKA robot was, even if it was in reference, it was vibrating. Okay, in the same plane. Okay, so these data, if we directly feed inside the control system, okay, the control system is also going to be unsafe. Okay, so before we get to give the system, okay, we need to make use of some sort of Kalman filter or something, okay, which will, in order to make this decision, okay, it will filter out as much as noise as possible. Okay, so we can see how it's going to work. Okay, so Kalman filter is already available in LabVIEW as a box. Okay, as a tool is available. Okay, which will be found as basically this is the implementation of control system. So we are going to find the control system, Kalman filter at one of the nonlinear systems or in some sort of operators. Okay, it will be available. Okay, it will be available the estimation. Okay, you'll be having some systems like this. The Kalman filter is available here. Okay, Kalman filters are available. Okay, extended Kalman filter. These can be used for your own, purpose. Okay, so like if I run this, okay, you're going to see this red color. Okay, this is basically measurement from an actual system. Okay, and based on this actual system, we are saying that we have to take decision. Okay, so what we do is, if you see the actual, measurement, you can see that it's very noisy. Okay, it is below. Okay, both distance and angle. Okay, it has a lot of noise. Using this noise, if you feed it to a control system and use it for plotting, it's going to be a problem. So what we do is we apply Kalman filter, okay, external Kalman filter, whatever. Okay, when we apply it, okay, it's going to filter the noise apart. Okay, again, it's an algorithm. Okay, and if you see after applying external Kalman filter, you will see that in between your data is coming. Okay, so instead of taking the noise, okay, it's taking the actual data. Okay, the blue is tracking the actual location. Okay, of the object. Okay, a true trajectory. A true trajectory is actual location. Right? The measurement is different, the actual position is different, and what your EKF is plotting is also different. Different parameters. But of course, all of these three things are plotting the object. By using a sensor, you are plotting here. Okay, after subjecting the measurement to the EKF, we are seeing the data in a blue to green color. Okay, and the true data is basically the simulated data which we are supposed to plot. Okay, so for that, we will apply Kalman filter. This is again a part of LabVIEW ecosystem. Normally, to implement Kalman filter, people will go for their own algorithm development. They'll do these calculations and stuff. But since LabVIEW has this built, it's best to make use of. Okay. So now that we saw about how we can make simulations using LabVIEW, okay, we'll see some more examples of the simulated environment. Okay, like this goalkeeper, we have like maze robot. Okay, which will go through the maze. So let it run first. It will take some time to load. And that's open. Okay, starter kit has open. Okay, if you open inside, there's something called multiple robots there. So if you see the list here, okay, in this robot, okay, it's going to have multiple robots. We have starter kit 2.0, 0, 1. Okay, 2 robots are there, and we have 1 up to obstacles. So everything is listed here. So in programming, we have to make use of the reference. We have to reference that particular sensor if you're going to take the sensor. Okay, and the model also has been created by using the XML. Okay, so the robot sensor is being written. Okay, by using that sensor data, your robots are trying to go through the maze. Okay, so if you run this program, I believe it will open the window. Okay, you can see that 2 robots will be trying to navigate through the maze and solve it. So someone has to write the logic behind it. Okay, so if you see, it is directly by default it's doing this. So it has to navigate through the maze. And it has to reach this, I believe. Okay, so it has to reach here, but I think it will still go here and search there. It will come back. Someone has to program this, right? So instead of directly getting this maze box and bringing inside my or any type of hardware, okay, this will directly we are able to simulate by using this model. Okay, the sensor data also we are able to see it. So I'll stop this. And code is not going to be much different. The only thing is because we have 2 robots, okay, we are going to have 2 robots instantiated parallelly. Okay, everything will be plotting, will be doing the path finding and stuff. Okay, but that's it. First we'll initialize the robot. Okay, then we'll say like right servo angle. Okay, again the algorithm is written to get the scan cycle and stuff. Okay, then by getting the servo angle, they are telling, okay, you have to measure the sensor distance. Okay, so sensor distance is basically ping sensor is in size, I believe. Okay, so that data they're just taking it up. Okay, so once they get it, by using that, they are calculating something. Okay, they are updating the distance. Then they are making use of, an algorithm again to calculate the driving distance, whether they have to go to left or whether they have to go to right. And so they're using all this information, they are again writing it back to motor. Like a feedback. It's like a control system. Okay, you bring the data in, you calculate certain stuff, and again you pull it back. And 2 motors are there, that's why they have used, if you have 3, okay, you can use 3. If you have 4, you can use 4. So this is running at 20 milliseconds, 50 hertz, every 50 hertz it will run. If your computer is capable of, much faster simulation, you can try reducing it. Now if I run this, it will run much faster. Okay, you can see scanning. So if the obstacle is nearby, you can see that the scanning is in field. Okay, based on the data which it receives, okay, it's going to avoid that obstacle. That's all it is. So I hope that was informative, okay, for the simulation. But now the other question is open-ended now. What type of hardware can we use in order to implement it? What type of hardware can we use in which is also controllable by using LabVIEW to implement the same type of programming and create a robotic embedded system to control all these motors and drives? So there should be something which is available as a part of LabVIEW ecosystem, right? So if you are able to simulate in LabVIEW, since LabVIEW is a programming environment, there should be something which is capable of implementing it as well. Okay, yes, we do have it. Okay, so that's why we make use of something called MyRio. Okay, we'll make use of something called Rio environment, okay, Rio hardware, okay, which is basically a combination of both, an ARM processor and FPGA, okay, which is capable of communicating with several sensors, okay, also create a whole closed-loop control system, as well as bring the data back to your computer. It could either be used as a like an IDAC, you can make use of it, or you can use it separately as well. Okay, you can dump programs in a robot. Robot means basically it will have its own embedded system, it will have its own way of thinking. Okay, it will have programs running inside it, right? So if you want to implement it, you can make use of this, MyRio. So how do you do it then? Okay, so in order to do this, first what we'll do is we'll know first what exactly is MyRio is. Okay, in order to work with MyRio, before I connect to my camera, okay, so first we'll understand what exactly is MyRio is. Okay, so just let me just open PPT. Okay, I'll get the PPT, then I will display again. Just give me a moment. So let me display it again. Present now, an entire screen, and I believe you are able to see my screen. So as far as now what we are seeing, okay, it was just simulation. Okay, and during simulation, you might have seen that, okay, if I show you this KUKA bot simulation, you might be seeing that we'll be accessing some sort of drivers. Okay, everywhere we'll be accessing some sort of driver. Okay, so right now these are all similar drivers if you see. Okay, it's all simulated drivers. Okay, what if we have the access to actual hardware? Okay, if we have access to actual hardware, how can we do the same thing what we have done in simulation, but in real world? Okay, to do that only, yes, we can do it, number one. Number two, instead of rewriting the same thing over and over again, okay, if you see here, we have this an example of a real world implementation as well. Okay, here we have simulated KUKA board, right? So in order to control a real KUKA board, okay, so there is a program written in LabVIEW only. Okay, and for real KUKA bot, you cannot see the stuff here. Okay, we don't see anything here. Okay, the reason is real KUKA bot means your real KUKA bot will be in front of it. Okay, but right now, let's say we don't have access to KukaBot, that's why we went for simulation. But if we had KukaBot and Rio also, okay, when Rio is a hardware, we'll talk about it more. Okay, it's a line of hardware in a national instrument, okay, which offers embedded control. Okay, we can connect this KukaBot to Rio and help Rio control it. Okay, so this is connected through the way called as EtherCAT. Okay, EtherCAT is again a connection. It is available as a part of industrial communication. Okay, so Ethernet-based field-based system. Okay, which will be normally used in automation. Right, so by connecting it via EtherCAT, we'll be able to send commands to it. Okay, so this is connected via EtherCAT, and we program it. Okay, so what we do is we use the same stuff. Okay, programming and all, if you see, okay, whatever we did using the simulation, the same functions only use, nothing different. Okay, only thing which we do differently is the initialization of KukaBot will be different. Okay, so here we will initialize the actual KukaBot. You see, we are initializing the actual KukaBot instead of using your simulation. Okay, if you see in the robotics, we have an actual KukaBot and simulated KukaBot. But the program will be same. Okay, so we'll do the same thing like, arm initialization or whatever it is. We will do parallelly. And here also, if you see, we'll be doing this velocity control. Okay, during the velocity control, we'll use a function called frame. Okay, we'll just convert the exact channel velocity into something a motor can understand and send it to the motor. Okay, the same thing only will do in the implementation part as well. Only thing was the whole thing was copy pasted from there. Okay, and only thing which has changed is if you are using a simulated KukaBot, okay, we have to specify the name of the KukaBot. But here, since one Rio can control only one KukaBot, okay, so they haven't mentioned any reference. Okay, and ultimately we'll close the reference of it, shut down, and your KukaBot internally will have electronics. We'll send command to it to stop the operation. But the program between the simulation and your actual implementation will be almost negligibly zero. Difference will be negligibly zero. Okay, so it will be same. What I mean to say, it will be similar or same. Okay, but let's say we want to know how to program this hardware. Okay, even though the simulation and stuff is same, okay, we need to look at some tangible, efforts, right? Like let's say, for example, there are some sort of sensors which are available. Okay, in the robotics, the KukaBot is connectable via EtherCAT, fine. But if you see, there are some device IOs like LiDAR and stuff, okay, which have its own, type of connection. Okay, like if I go to an actual device IO and see that it's LiDAR, okay, so during the initialization, I may have to tell what type of protocol I use. Okay, so apparently it uses something like VoIP. Okay, NIGSA means it should be connected via, my RS. So I have to use RS-32 to get the data from it, right? So if I use RS-32 to connect it, okay, then I need to know how to program RS-32. And maybe your computers will come with RS-32, but some type of embedded controllers also will come with RS-32 or CD4. Okay, so right now robots should be autonomous, meaning we should not control it by connecting a robot to a computer. Or rather, you should use some sort of hardware which has the serial port or whatever protocol-based sensor. Okay, it needs to have the capability to connect it, control it, and get data from it. Okay, so I thought I heard someone. So if you have doubts, please do let me know in the comment section. I'll answer it. Now the question is, how do you program hardware like this. So in order to start programming, let's say right now, if you want to start smaller, okay, on how to program an embedded system using LabVIEW, okay, we have a line of hardware called as NI-MyRio. And I'm sure most of you have already been aware. Okay, maybe your university has one. Okay, maybe you own one. Okay, I'm not sure. But there is a hardware like this. This is capable of implementing an embedded system. Number one, it has an embedded system. Number two, it has protocol-based, IOs, which will enable us to connect with robotic sensors. Okay, the sensors which robots interact with. Okay, so these type of hardware are called as NI-RIO. Okay, it stands for reconfigurable input output. Internally, it has, an ARM processor inside and FPGA, meaning if you want to do some complex processing, this particular hardware should be capable of handling it. Okay, and it also has USB port, meaning if you want to connect a camera to it, okay, it should be able to do it as well. Okay, so that's why this MI-RIO is available. For which we will be seeing demo today. Okay, so we'll be seeing how we can make use of the RIO platform to acquire data from some sort of protocol-based sensor, and view it in the environment. Okay, then we'll be seeing how we can control some motors. Okay, typically that motor could be an actual robot. Okay, send the signals from your MyRIO to that motor. Okay, and view the responses here. Right. So now let's start with. Then we'll see how we can deploy code inside RIO. Okay, then it will be running autonomously. Okay, so these are things which we are able to see. Okay, but let's understand what exactly this RIO hardware is. Okay, so this is how RIO hardware will be looking like. Okay, they basically after they schedule the break, we'll connect the camera and we'll see what exactly I'm doing here. But let's understand. Okay, so this why MyRIO is the preferred platform. So to understand that, if you see MyRIO has a portable reconfigurable device. Okay, RIO. Okay, it stands for reconfigurable. Okay, the reason why they gave us reconfigurable is that FPGA. Okay, meaning if you use an FPGA, you can make use of one IO for several things. Okay, you can reconfigure it, the reconfigurable digital input output to act like DIO, or you can use individual DIO pins as something which you wanted to be used as. Maybe you can use it to generate PWMs individually. Maybe you can use it to as a custom data transfer device. Okay, so whatever it is. So this device should be capable of doing that. And by doing this, what you can achieve is, okay, you can design a control system. Okay, because it has something similar to MyDAC. Okay, yesterday I'm sure you have seen MyDAC. Okay, MyDAC is capable of acquiring and generating signals. So when you're able to acquire and generate signals, you can implement a control system. Okay, so you'll generate some signal, you'll give it to a device which you're interested in, and when you give a signal, okay, that system will respond to it. Okay, and once it responds, you will again sense it and get the feedback into your control system. Okay, again based on this signal error, okay, you will try again to adjust whatever needs to be adjusted. Again, this will keep on repeating, and this will be finally this will be the control system. Okay, so MyRIO, this platform is used for embedded system. Okay, it can read sensor data. Okay, which is basically it could be a sensor data from an analog signal, a digital signal, so on and so forth. And since it has an ability to connect, it has ability to act autonomously, it makes it perfect for robotics. So why MyRIO? Okay, so basically this MyRIO has analog input, meaning you can connect multiple sensors to it. Okay, yesterday whatever sensors you have seen, okay, same sensors can be connected here as well. And you can send the analog output as well. Okay, digital input digital output, same thing. Okay, so it has capabilities of MyDAC. Okay, but MyDAC, if you see, you cannot program a MyDAC and dump code inside it. Okay, so MyDAC will be an extension of your laptop. That's all it can be. But if you want to get data from a sensor, process the data internally itself, then you want to control something, then we will suggest MyDAO is the proper, because MyDAO itself is a computer. It also has its own, data. I mean, it has its own IP address. Okay, it has its own operating system. Okay, so meaning you can develop code, and if you dump it, the operating system will take care of the execution. Okay, so it has a Xilinx Zinc inside. Okay, Xilinx Zinc is basically a combination of ARM processor and FPGA. Okay, Xilinx is the company which produces FPGAs predominantly, but this particular Zinc family, okay, they are basically used to do, it has both ARM processor inside it internally and FPGA inside it. And also this MyDAO, since it does not have display like MyDAC, okay, at least MyDAC is connected to your laptop directly to program it. MyDAO sometimes will not have display also. It is used to run headlessly. Okay, headlessly it will run. So in order to indicate the status, okay, so we'll be having some onboard LEDs. Okay, like power LEDs we'll have. Okay, we'll have something like power LEDs. Okay, so we not indicate power. And we have status LEDs. Okay, maybe let's say you're writing a program, okay, of controlling some motor. Okay, and maybe that speed of the motor is exceeding some limit. Okay, so you need to indicate it somewhere. So what you can do is you can make it as a status LED and display, okay, your speed is going too fast, maybe slow down. Okay, and moreover, this MyDAO has Wi-Fi on top of it. Okay, you can wirelessly connect your robot and see its status. And since it has Wi-Fi, you need not connect it to your laptop only through Wi-Fi. You can basically connect it through your cell phone also. So you can connect your cell phone to your MyDAO, and you can create a kind of, you can use some sort of app application, send command from that application to your MyDAO and control it. Okay, so that also can be done. So there is also a push button. If you intend to stop whatever is happening inside, there's a push button. And these are onboard devices. It's not like you have to use the push button only to initiate DIO. You can also use one of the available IOs also. Okay, so you can use buttons to switch on DIOs also. And to switch on stop Wi-Fi also, you have a separate button. And on top of this, since you want to implement robotics, on top of robotics, you need an accelerometer. And to get the data of accelerometer also, you have, instead of creating a separate accelerometer, you'll have like accelerometer separately, inbuilt accelerometers available. And not to mount this hardware separately, okay, you have this mounting hole separately, which you can mount it on top of. And for programming, you have separate USB ports. And let's say you want to connect a USB to log some data, or you want to connect, a type of camera. Okay, so that camera can be connected to MyDAO. Let's say you want to do a line following robot. Okay, since if you saw we were able to simulate some camera, then it would make total sense for us to connect an actual hardware which is capable of doing this USB, right? So this MyDAO also has capability of USB, USB cameras. And more importantly, since it's going to be used for robotic system, you need to supply separate power supply to it. At least MyDAC, if you see, we were able to connect it to, because USB power, only power it needs to be in your laptop. But since MyDAC has lot of inputs and outputs, you need to power it by using your supply power supply. And separate IOs, if you see, you can see that the separate IOs, you have like MyDAC based connector on the left hand side. Okay, on one side you'll have something similar to MyDAC. And the other side, okay, these are the MIDA connectors. Okay, same thing only it's also here. Okay, same connectors only it also is here. Okay, so only thing is MIDA DIO can only be used as a DIO, but if you see MIDIO, it can be both used as DIO as well as an encoder connector also, because most of the time MIDIO will be used to implement a robot, meaning you need to get data from motor. Okay, so to control motor you use DIOs. Okay, to get data back you need counters. Okay, counters basically encoders. Okay, to get the speed at which the motor is rotating and those stuff. Okay, you need an encoder. Will be used. And to control the speed of the motor also we need PWM generators. For MIDAS also we have PWM generators, but MIDA has you have two types of PWM generators. So it's absolutely the whole control system kit itself on top of MIDA. And this is only on MIDAS side. We call MIDAS connector as MSP, or also called as mini system port. If you want more, okay, totally we'll be having 33 plus 36, 66. 66 plus 20, 86. Okay, 86 pins. The MSP1 port, and we have this MSP port, also called as MIDA expansion port. We have two ports. Okay, so these two ports are identical. It has other pins. So like 3.3 volts, 5 volts power supply. Okay, for most of your sensors, we need 3.3 volts or 5 volts. If it's a normal sensor, okay, 5 volts will be the one. There are some protocol-based sensors like I2C sensor or SPI-based sensors. Okay, these are protocols. Okay, so if you want to get data from that, we'll be using 3.3 volts. So for that also we have supply power. Okay. So now, what exactly is the architecture behind it? So since I already told about your Rio has process, and the processor will not be directly connected to any of the inputs or outputs. Your architecture will be something like this. Your FPGA will be connected to IOs because the FPGA are mostly more deterministic. Okay, and easily interact with the IOs. Okay, it does not. It only thing it has this propagational delay. So maybe for your control system, we need to do very high speed acquisition and generation control. So in the loop rates of megahertz, control loops will be in terms of megahertz. So if you want to be deterministic, sometimes FPGA code will be the one which we have to go for. Okay, and most of the people will be like, okay, so if you want to program FPGA, I need to learn VHDL. And for a robotic engineer, learning FPGA, VHDL or Verilog is a roadblock. Okay, in order to implement this application, if he has to learn VHDL or FPGA, FPGA-based programming, it's going to be a significant amount of roadblock. And we don't want that roadblock. Just because we don't know that, we should not be able to implement that, but it's going to be a bad thing. So in order to speed up the process, we already know LabVIEW. And by using LabVIEW, we already told that we can program some embedded systems. Okay, then it makes total sense that since the FPGA were already told us as a future, okay, we can program LabVIEW itself, maybe FPGA by using LabVIEW only. Okay, LabVIEW only can be used for programming FPGA. The toolkit called as LabVIEW FPGA will be responsible for this. Using LabVIEW FPGA, we will program the FPGA. Okay, it will compile directly to bit file, and you can use it. And of course, maybe programming using FPGA, normal VHDL. Okay, if you know how to program using VHDL, it will be faster. Okay, because converting VHDL to LabVIEW, some FPGA code might not take that much time for compilation. Okay, but compilation of FPGA code and LabVIEW to FPGA code supported by FPGAs. Okay, so that is compilation time is going to be significantly slower. Okay, compared to compiling VHDL to direct FPGA. Okay, so that is going to be faster than what LabVIEW does. Okay, so FPGA will be connected to processor. So when you want to interrupt processor with the IOs, okay, data will come to FPGA only. So this is called NI RIO architecture. Okay, we don't know much about it, but I'm just explaining this what happens inside. But rest assured, you can also program processor to get data directly. We don't need to learn FPGA programming to get data. Okay. So let's see how we can make connectivity between your LabVIEW and FPGA. Okay. So first, let me show what exactly is in front of me. Let us take the camera. I believe camera is somewhere over here. So sorry about that. Again, I got disconnected. I believe I told I will be connecting to webcam. So just give me a moment. I'll just reconfiguring it. I believe webcam should be visible. The camera is off. So let me just switch it on. And this is what I have in front of me. Okay, this is my RIO. Okay, so this is the hardware platform. Okay, which we have in front of us. Okay, so yeah, so this is the one which has this MXP connector, which is similar to MIDAC. Okay, and we have this MXP connector. Okay, which makes it totally compatible for any type of robotic process which is required for us to be developed. Okay, it also at the back it has this accelerometer. Okay, if you want to mount it and do something with it, you can basically do it. Okay, so now our objective is to know how to make a connection to this particular hardware. Okay, so I'll remove it now and reconnect it. Okay, when I do that, this pop-up window will come up. Okay, so let me just share the screen now again.
I'm really sorry about this. Interconnection seems to be very bad here because of rain. Okay, so we'll continue the session again. So what I was about to say is, uh, how do you make connection to your rear now? Okay, so we have already connected to your camera. I already connected to my USB. Okay, and when I connected to USB, what I said was, I'll share screen first. And when I press my screen, here I will see that I have this pop-up. Okay, which is available here. Okay, this says, okay, first legend started wizard. Then I have an option called as go to LabVIEW. Okay, so I will program this MyDO using LabVIEW only, nothing else. Okay, I can also configure my MyDO and I can launch again install wizard, etc. Okay, so I have plenty of options regarding that. Okay, now I just go to launch getting started wizard. And then I'll browse for it. Okay, it's checking. Okay, whether software is there. Okay, basically your MyDO, I already told that it's an embedded system. Okay, meaning it will come inside itself. It will have LabVIEW. It will have the toolkits, whatever is required to model. Okay, everything will be installed inside. The only thing this MyDO is actually a computer, but it does not have a display. Okay, and the type of OS which will be having inside, okay, will be Linux. Okay, Linux real time will be installed. Okay, real time OS will be installed. Okay, so when you have a real time system, it's going to be very deterministic, right? So that's what makes it, far more reliable than Windows operating system, because when we use the Windows operating system, you could see that even my computer, okay, it's very slow. The reason being, it's Windows, so priority will be given for everything at the same time. Okay, you can of course make use of something which can reduce the priority. Okay, but it will not still be deterministic. Okay, so for robotics, the most important thing is to acquire sensor data, which we see over here. Okay, so if you see, I have this accelerometer. Okay, I can show via my camera also. Okay, what I'm exactly doing with my Rio here right now. So I'll turn on the camera. And right now, turn on the camera. Okay, so you should be able to see that I have my Rio here, and I believe you should also be able to see my screen. And when I make some changes, okay, so in this device, okay, you should be able to see that I'm able to see the changes in the accelerometer as well. Okay, so when I change the orientation of my Rio, okay, when I'm changing the orientation of my Rio, okay, so I should be able to see the device changes as well. So let me just plug this somewhere. Yeah, so I made it stationary in the camera. You can see that when I make some changes, okay, so I'm able to see the reflection in my getting started wizard as well. So this is to show that MID has some inbuilt sensors. Okay, so one of them is accelerometer. There's accelerometer data. We are not looking anywhere else. We are looking inside the computer. Okay, because MID does not have a display. Apart from that, you can see that there is user programmable LEDs. Okay, so which can also be programmed by user. So by using these buttons, okay, I can be able to change this status of those LEDs. And apart from that, at the back of the Rio, I have this button, user button, okay, which I press. When I press it, you can see that the display is coming on to the computer. Okay, I'm reading data via the USB. It comes to the my Rio display, and we are able to see the data. Now this is developed by using LabVIEW only. Okay, the data you are seeing is basically, if you see this button, LED, this button on a LabVIEW stack. Okay. So yeah, if I give next, it's going to ask me whether I want to start the first project or what I want to do. Okay, those things are available. Now, what I'm going to show is, I'm not going only going to show you the stuff which is available inside the programming. Okay, let me show you how we can configure the IDE. Okay, since it's going to be autonomous, and I told there is a operating system inside. Okay, and robots need to have some operating system inside. Okay, we need to be able to configure it. Okay, so yesterday we saw something called NIMAX, I believe. Okay, I'm not sure if NIMAX was shown. Okay, basically NIMAX was used to configure the NI hardwares. Okay, so basically we use it to configure everything. And this is no exception. We use NIMAX to configure EOS. The location where we look at NIMAX and the location where we look at MyRio is different. The reason is, if you see, my DAX yesterday got already connected. Okay, it appeared under your device and interfaces. Okay, because it's an extension of a computer. Okay, but MyRio, on the other hand, as I told you, is a separate computer. It's an embedded computer, meaning it will come under something called remote systems. And you'll see that MyRio is there. Okay, so basically you can even connect another computer under here. okay, which can be broken by using LabVIEW. And under the MyDeo, you will have device interfaces again. Okay, and under MyDeo, you will have device interfaces, but now this will be used if you have a USB connector or some other MyDeo connector or MyDA connector or whatever. Okay, but under my device interface of MyDeo, you will have a FPGA. Okay, this is basically FPGA. Okay, you can update the firmware of the FPGA or whatever it is. Okay, then you'll have, since it's a computer, it has serial ports inside. Okay, so it has 2 serial ports and configured for this baud rate, data bits, parity, everything is configured. And moreover, you also have software inside. Okay, so if you look at this, basically, if I want to look at my computer's specifications in NMax, I'll go to my system and show me, okay, it's like my computer name, my vendor, um, my model, okay, operating system, everything will be shown. And similarly, if I click on this MyDeo 1900, it will show me the system settings by default. Okay, my MyDeo's name, okay, the IP address of MyDeo, okay, of course, it is connected, even though it's under USB, okay, it's like there's a USB to Ethernet connector inside. So your MyDeo will be assigned the IP address. So you'll see DNS name, okay, vendor, all the information. But most importantly, you'll see operating system, okay, which says NI real-time Linux, ARM version 7, and it says status. Okay, because it does not have display, we don't know whether it's properly running or not. So it says current and running. And using NIMAX, since it does not have a display, to configure it, we have this software called NIMAX. Okay, I can even change something like, how to make the connection. Okay, like whether right now should I connect it to wireless network, right now it's configured to connect to a wireless network. Okay, so that's why you can see the color of the LED is blue color. Okay, the Wi-Fi LED is blinking. Okay, it's blinking in blue color. Okay, I can, however, change it to like create wireless network, act as a hotspot. Okay, and I say Rio. Okay, I'm gonna save it. Its color should now change from blue to red. You should be able to see that it's red. Okay, if you see my camera. Okay, so I can either make it as a master or I can either make it as a slave. So that's how we can play around with, you can configure my view. And as I told, this also already software inside. Okay, you can also install what are software is permitted. You can see what are the softwares already installed, or if the softwares are not installed, okay, you can install it. And if you see, there are wide range of connectivity options. Okay, you can even connect your MyDeo to internet because it has Wi-Fi. Okay, it doesn't make sense if you're gonna connect to internet. Meaning you can connect it to one of the cloud. Okay, maybe you can wirelessly access these robots which you're building using MyDeo, paving way to Industry 4.0. Okay, so Industry 4.0 can be implemented using Rio systems and LabVIEW. Okay, so protocol supports are available, network support is available, everything is available inside the area environment required for building and remotely operating a robot. Okay, so then what? What next? So next is basically after we are familiar with Rio, we'll see about how we can configure Rio to acquire data and generate data. So Hello? Hello? I think now you should be able to hear me. Yeah. So thanks for that information, ma'am. Very thank you. So yeah. Now if you see, I have this project, okay, MyRio, okay, and I can make use of this template in order to speed up the process of my application development. Okay, instead of developing from scratch. Of course, for everything there will be a blank project as an option. The reason is if you want to develop from scratch, also you can do. But right now, let's say everywhere time criticality is important, so I can make use of this project. And also FPGA also, if you want to program custom FPGA based project also will be available, which you can freely make use of. And if you see very clearly, you can name the project name, whatever project name you want to do. Okay, let's say if you want to build a robotic interface, okay, you can build it. Or let's say I'm just going to name it randomly, FPU, and I can say where I want to store the data. Okay, I'll save it as I would new folder. I will name it as RIO. Save it. I'll go inside. I'll name it as RIO again. Save. Okay. Then I can, if required, I can program it through USB. Right now, since I connected Rio through USB, I'm seeing it there. Okay, I can also, however, program it using Wi-Fi. Okay, if I can remotely deploy code, that is also one possibility. I can also do generic target. Okay, meaning I don't need to connect to a MyRio to program a MyRio. Even without having a MyRio, I can program. But of course, I cannot visualize data. That is one problem. Okay, then lastly, if you see, I can see a list of IOs available. So when you see an embedded system, okay, for robotics, there are a lot of things which are required. Okay, like I want to connect control motors. So basically, if I want to switch on and switch off motors, I have DIOs, 40 DIOs available. And 40 out of these 40 DIOs, you can make use of 8 of them as PW. Okay, so 32 minus 8, I mean 40 minus 8, 32. 32 can still be used as a separate DIO. Okay, if you want to control motors, possibly you will be using PWM, maybe to control speed. Okay, so typically that could be a normal DC motor where you have to adjust speed, or to adjust the direction. Okay, you can use a servo motor maybe. Okay, so servo motors, 8 servo motors you can control by default. Okay, by default you can control 8 motors. And using the encoder, you can read the speed of 4 motors. Okay, so normally a rover or whatever type of four-wheeled motor robot, if you want to control, when a measure, you can make use of 4 encoders. Okay. Apart from that, you have like 4 LEDs, okay, 3 accelerometers, and protocol-based sensors. Okay, so protocol-based sensors are like very famous among robotics. Okay, because if you go for non-protocol sensors, then you'll be restricted to only 12 analog input, 8 analog inputs. Okay, those kind of things. But let's say if you want to go for something custom, okay, SPI means SPIs will be a bus, okay, from which you can transfer receive data. So you can make use of, you can connect in one bus, you can connect as much as required. Okay, typically SPI will be like 3 wires or 4 wires. Okay, one will be enable and disable. Okay, meaning using this 40 LED, 40 DIOs, okay, you can enable or disable whatever sensor you want. Okay, and you also have I square C. You don't even need to have 4 wires. Okay, I square C means individual sensors can have individual address. Okay, and by pinging that address, your I square C will return data. Okay, so you have commonly used embedded protocols. UART also you have. Interrupts also you have. So everything is programmable by using LabVIEW. That's the one advantage. Okay, when you have LabVIEW, you don't have to worry about how I'm going to configure these things. Okay, do I need to learn embedded C, or whether I need to learn Python based programming? No. Okay, and programming itself is not really a problem in LabVIEW, right? So this drag and drop, configure, it's done. So we finish it off. So it'll prepare the code. And here you can see my project will be created. And in my project, LabVIEW project is typically used to organize my file structure. So whatever program I write under, if I want to run it under my LabVIEW's computer, I will write under my computer. And if you want to access my Rio, I will write VAs under Rio also. Okay, so Rio is, I can say generically Rio. So if I want to control a robot, okay, to which my Rio is connected, and Rio is only which is going to send signals. Okay, in that case, I can typically make use of VAs under Rio. Okay, so now like I can, if you see, as I already told you, this is a template, and template will always have a starting code, okay, to just kickstart your application development. Okay, so here they are saying, okay, you just need to initialize, process, and close. And they also given a example code which reads the accelerometer data and plots it. Previously, we saw accelerometer data in the form of slide. Okay, now we are seeing in terms of graph. Okay, so I can run this program. Okay, when I run this program, you can see that it is whatever code I have written in my computer is getting compiled. Okay, deploying is taking place. Okay, it's getting compiled, and this data will be put inside my Rio. Okay, it is happening as we speak. The code is getting transferred from my computer to LabVIEW, in my LabVIEW to my Rio. And it says close on completion. I'll not give it. Okay, I'll just close it. And once I close it, I'll get the data from my accelerometer to my VA. So you can see that right now my Rio is stationary. Okay, so that's why I'm not seeing any readings. Okay, but when I change the orientation, okay, when I make some disturbance, you can see that some changes occur. Even if I like knock on my table in which I'm keeping my Rio, okay, my accelerometer is going to produce significant amount of acceleration. Okay, because that's what accelerometer does. So if I do some noise, okay, it's going to do that. So accelerometer is basically going to measure the amount of acceleration either due to gravity, okay, or either due to vibration. So right now, the other two are 0, but if you see the green color one, because z-axis is basically showing 1. This 1 is basically nothing but the acceleration due to gravity. Okay, that is 9.8 meter per second square. That is considered as 1g. Okay, and since I placed my Rio flat, okay, the z-axis is subjected to acceleration due to gravity. It is trying to fall down, but my table is holding it. Okay, if I change orientation, Right now, instead of flat, okay, that's why it's z-axis the data, the um, acceleration to gravity is. But instead, if I just place it like this, now the acceleration to gravity is going to be falling on x-axis, but negative format, negative fashion, because I place it reverse. Okay, I can place in this direction. Now you can see it's subjected to 1g in x-axis. Y-axis means I have to place it like this. So this is what your accelerometer can do. So the sensor data, IO data, everything can be brought inside your LabVIEW. Okay, once you get an appropriate sensor. And this is happening inside the embedded system. And what is happening is why you're seeing the data in your computer is the very simple reason. Since you're programming using computer, your computer takes care of transfer of data from your computer and from your video to your computer. But the execution of the code is happening inside Rio only. After sending the data from your Rio to your computer, you're displaying it in your computer. And how do I say whether the program is running under my computer or my Rio is on the right hand and the bottom left corner of the front panel, you can see that it says my Rio 1900. Your code is running under my Rio 1900. Okay, so that's the proof is to show that your my Rio code is running under stuff. Okay. And for that, we didn't write any complex embedded system. We didn't write any complex computation of anything. Okay, only thing we did is we saw the template. Okay, here we'll be having accelerometer data. Okay, and of course, we can access all this MyRio data in a panel called as MyRio. So here we can see each and every piece of information. Okay, like analog input, analog output, digital output, button, LED. These values also can be seen. Accelerometer data. That's what we are seeing here. And when we are configuring this, we don't need to learn much about embedded system programming or embedded C programming. If you want analog input data, you just drag and drop this analog input function. As simple as that. Okay, we have lower functions as well. Okay, just like how LabVIEW MyDAC has lower functions, this also has lower functions. Okay, like for example, if I want to glow an LED, that also I can do. Okay, I just have to drag and drop this LED. And this is going to do stuff. Okay, I can control how much LEDs I'm going to control. I'm going to work with. Okay, let's say all 4 LEDs I want to control. I can also do that. I can also disable one LED if required. I can name this as X, Y, and Z. So some functions in LabVIEW will open a configuration window and I can say what exactly needs to be done and it will be done. Okay, so to control all this X, Y, and Z, I can create an LED and a button, a front panel. I can name it as X, Y, and Z. And I can connect X to X, Y to Y, and Z to Z. Okay. Now this program. Now since I made some change, I have to again save it. Again the program will compile. And everything is graphical. That's one more thing. This VA will be put inside the LabVIEW video. Okay, and right now you can see in my camera, okay, accelerometer is working parallelly. You don't need to worry about that. AD control also can be done. Okay, programming using LabVIEW. And instead of using this LED, let's say I want to like based on the accelerometer data. Okay, I want to control the LED values. So whenever value of the accelerometer goes above 0.5 or something, okay, I need to blow the x-axis, y-axis, z-axis. Again, since you already know basic LabVIEW, we just get the data in the form of dBl from this accelerometer. Okay, we just need to do a comparison. Okay, we can select whether the value is greater than or equal to whatever it is. So whenever this value goes above greater than 0 equal to, we'll do a constant of 0.5. Okay, I can have two more copies.
Rajkumarji, can we take break now?
Now, sir, I will just finish this and we'll go for it. Just 2 minutes will be done. It's okay.
Okay, okay, okay.
So x-axis, y-axis, z-axis. Okay, so I just need this embedded system to tell me that whether accelerometer value is going above certain value. So I'm just getting the data, comparing it. Then the value is Boolean, it's going to be true or false. Instead of using a button to enable indicate it, I'm using this condition here to indicate it. Again, I will change. Right now, by default, one LED will be glowing, z-axis LED will be glowing. Okay, because it is flat, it's going to be above 0.5. And the last LED is, will be glowing. But I can change the orientation and corresponding LED will be glowing. Okay, by changing the orientation, I will not be able to see the LED. But maybe right now I can see, yeah. Okay, different LED is glowing. So on and so forth. So that's about introduction to Rio. Okay, using Rio, we will see much more things. Okay, apart from simulating, if you want to implement it, this is one of the ways. Next, we'll see about protocol implementation, how we can make communication with MyRio via maybe mobile, okay, or control motor or something, whatever it is. Okay, we'll see it after a break of, I believe, 1 hour. And we'll come back. So stop presenting. Stop camera. Yeah, I believe we can go for a break, as I told. So I'll join after break.
Sir, so we will take break of 1 hour, and after lunch we will
Yes, sir,
join
sure.
at 3 o'clock. Okay.
Yeah, sure.
So